In question 4, a 79 kilogram astronaut is orbiting the Earth at a height of 600 kilometers above the Earth. And so I think you've all seen people on spacewalks. They're floating, they're weightless. They just have this freedom and they move about as if no force of gravity is acting on them. And the question is the force of gravity acting on them? If you had to guess, this person, this astronaut, what is the force of gravity acting on them? Is it 0? Is it half of what they would experience on the Earth? What is it? So this is what we can now calculate by using our new equation. So he's orbiting at a height of about 600 kilometers above the surface of the Earth. But remember, the surface of the Earth itself is 6.38 times 10 to the 6th meters away from the center of the Earth, right? To the center of the Earth. So what we're going to do is use our equation, Fg equals G, mass of the astronaut, mass of the Earth, divided by, and now we're going to talking about the distance between the astronaut and the Earth, center of the Earth squared, right? So we're going to have to add this 600 kilometers to this 6.38 times 10 to the 6th. So we'll just make sure to be careful about our units here. So plugging all this in, we get G 6.67 times 10 to the negative 11 times the mass of the astronaut, which is 79 kilograms. The mass of the Earth, this is a given, 5.98 times 10 to the 24. You can always use that number. It's something, if they don't ask it, if they don't give it to you in the question, it's just assumed you're going to look it up. And I can see here, I've already changed the number I'm using. This one from the previous problem, I've been using 6.38. This says 6.37. So, I mean, either one. For this problem, I'm going to use the number that I give you so that hopefully our answer will be accurate. So when I find the distance to the center, I'm going to do this 600, but it's in kilometers. So I'm just going to make it in meters, 600,000 plus 6.37 times 10 to the 6th meters. And then I'm going to square all that. So this is kind of a doozy to put in your calculator. So just really be careful. And a lot of the times, if you get it wrong, it is a calculator issue. So let me plug this in, times 79 times 5.98 times 10 to the 24 divided by, and then don't forget to use parentheses, so 600,000 plus 6.37 times 10 to the times 10 to the 6th, and then close parentheses squared. And I get 648.6. So it is a little different than, so this one says 647. I wonder if I did use the old number for this. Anyway, so I get 648.6. What did you get? I don't know if you used, which one you used. Now let's compare this to what we would get at the surface, which is mg. That equals, the mass is 79 times 9.8. If I just plug in those numbers, I get 774 newtons. So comparing these two together, I can see that 648.6 over 774 is about, so let's see, 648 divided by 774, it's about 84%, 83.7, 84% of his gravity. So it's kind of remarkable when you think about it. All those images, when you imagine that he's weightless, he's actually not weightless at all. His Fg is 84%, the value it has on the surface of the Earth. Remember that concept of weightlessness equals normal forcelessness, right? Fn lessness. If the Hubble's falling, or orbiting, and he's orbiting. There's nothing to exert a normal force on him. So he has no normal force, so he has no sensation of weight,